We're celebrating today the Spitzer Space Telescope. Joining us tonight, Mike Werner and Pete Eisenhardt, who are both working with the Spitzer Space Telescope. And let's bring up our speakers. Thank you, Michael and Peter, for joining us. Oh, and yes, prop. Get this lovely book in our bookstore, More Things in the Heavens, which is about the Spitzer Space Telescope and the amazing things you guys have learned and the journeys of exploration that you have taken by being able to see what Spitzer sees. So let me hand that back to you so I don't steal your copy. Why don't you tell us all about the Spitzer Space Telescope?
Okay. Hello, everybody. I'm Michael Werner. I'm the project scientist for the Spitzer Space Telescope. I've actually been working on this project for 43 years, if you can believe that. I'm delighted to be able to tell you about Spitzer and about our book. I'm here with my colleague, Peter Eisenhardt. It's always a pleasure to speak to people about astronomy, and I'm reminded, just a personal note, that after the Loma Prieta earthquake in San Francisco 25 or 30 years ago when the Bay Bridge pancaked and it was a dark and stormy night, I was speaking at the planetarium in Golden Gate Park, and there were hundreds of people there to hear me. I mean, hundreds of, a goodly crowd, and that just reminded me of how interested people are in astronomy. I'm well aware of the fact that we work for you in this business, and I'm pleased to be able to tell you about what we've been able to do. So here you can see a picture of great observatories, which was a concept developed in the 1990s to have observatories working across the entire spectrum. This is what was called CERTIF at the time, is now Spitzer, working in the infrared. In visible light, we have Hubble. In X-rays, we have the Chandra Observatory. In gamma rays, the Compton Gamma Ray Observatory.
Where's the Webb telescope on that?
It hasn't. That was not even a gleam in its pappy's eye at that point. But in this wavelength region, it would be here, bridging the gap between Spitzer and Hubble. If I understand the question. This shows the atmospheric transmission. Of course, much of the infrared is blocked. It also shows the fact there's a thermometer at the bottom, and all objects in the universe radiate at a wavelength which is dictated by their temperature. And cooler objects radiate the infrared, warmer objects in optical light like the sun, and still warmer objects, energetic things like supernovae, might radiate X-rays. You also see the...
Your mic flipped under.
Oh, I'm sorry.
Not a problem.
So you can sort of see here that you might see different things in the infrared than in the visible, which is why we need this family of telescopes. And that's illustrated very nicely here by our dog, Rusty. So Rusty is an ordinary dog. The lower image is the visible light image of Rusty. In visible light, what we see is scattered sunlight or scattered room light. If you turn the lights off, you don't see the visible image. The infrared image at the top, we're seeing Rusty where the radiation is indicative of the temperature of Rusty at various regions. And so you can see that near his eyes and his mouth, closer to his blood supply, it'd be a little bit hotter. And from the temperature scale on the right, you can see that corresponds to more infrared radiation. And where his fur is very thick, like towards his tail, it's cooler, and you see less infrared radiation. And since Rusty is a proper dog, he has a cold nose. Okay, so things look different in the infrared than in the optical part of the spectrum. That picture was taken with a night vision camera, perhaps, or with a infrared camera similar to the ones that were used on the Spitzer Space Telescope. So when we look at the infrared in terms of astronomy, there are several principles which we exploit in giving the unique characteristics of the infrared part of the spectrum. One is, we call this the old, the cold, and the dirty. That's a previously unreleased Clint Eastwood movie. But the old refers to the fact that because of the expansion of the universe, light is stretched. In more distant objects, the light is shifted further and further out into the infrared. So the visible light from very distant objects comes to us in the infrared part of the spectrum. That's illustrated here. When I take an optical image on the left and add to it an infrared image, you see this, that's called a cluster of galaxies. A bunch of galaxies clustered together by gravity, clearly seen in the infrared because of the fact that their light comes to us now in the infrared. That's way more than halfway across the universe that we're looking to see this cluster, and Peter will be talking more about this later on. The cold refers to the fact that things which are too cool to radiate an optical light, like our sun radiates optical light. It's at a temperature of 5,000 degrees Kelvin. This is a picture of what's called a planetary nebula, which is a late stage of stellar evolution where a star like the sun has shrunk to a cosmic ember called a white dwarf, and in the process puffed off a cloud of gas and dust. And around that star, we see this red bubble on the right in the infrared image, which is produced by radiation from dust, puffed off by, this dust is probably the remnant of a solar system around the star when the star was more sun-like, and is heated by the star to a temperature of perhaps 100 degrees above absolute zero, plenty warm enough to produce a lot of infrared radiation, but not warm enough to produce any visible light. So that's the cold. And finally, we have the dirty, which alludes to the fact that cosmic dust, little tiny particles of sand and graphite, soot, organic materials, are ubiquitous constituent of astrophysical systems. And this interstellar or circumstellar dust has the properties that it's opaque at visible light, but often transparent in the infrared. So this is an image of a region where stars are forming. Stars form out of dense clouds of dust and gas. In this visible light image, you can see there are lots of areas, particularly a little bit to the right and below, where you don't see much. But when we look at the same region in the infrared, you see all these stars there, which are not visible because of the interstellar dust absorbs their light in visible wavelengths, but you can see them in the infrared because the infrared light comes through, and we can see the stars in the infrared. At the same time, as was the case for that cloud of dust around the star in the planetary nebula, sometimes the dust is heated by starlight to a temperature where it can radiate in the infrared. So interstellar dust is a infrared astronomer's best friend. So going back one more time, visible light, don't see much. It's interesting enough. And here in the infrared, you see a spectacular image. I might add now that most of the images we'll be showing you are images from the Spitzer Space Telescope. They were obtained at infrared wavelengths, which you couldn't see with your own eye. Now, the reason we convert these into the infrared is because into visible light. We take these infrared images and with well-established protocols convert them into visible light for three reasons. One is they're awfully pretty to look at. The second is you wouldn't be too impressed if I showed you a bunch of ones and zeros. And the third reason is that people who, as you grow more and more familiar and comfortable with what's going on in these environments, you can draw inferences about the nature of the processes and the conditions very, very readily. And here, for example, in the upper left, the red emission comes from a class of molecules called aromatic hydrocarbons that we'll be hearing more about, that are ubiquitous in space and that Spitzer has seen lots of radiation from. And those aromatic hydrocarbons are excited by stars on the main sequence, like our own sun. As you move down to the right, the objects we see in the infrared have more the character of young and forming stars, still embedded in their natal cocoons. And so our inference here is that there's a wave of star formation propagating from the upper left to the lower right, where each generation of stars encourages or induces the collapse of the adjacent material, which then goes on to form another star, and so forth and so on. So this infrared stuff is pretty exciting, and you might say, well, why don't we throw an infrared detector on a big telescope like the Palomar telescope and let's go to town? And in fact, people have done that very successfully. I've done it myself. But when you do that, you lose sight of the fact that the surface of the Earth is a poor environment for infrared astronomy. And to do that, I've got this little story here. These are pictures, in fact, of the Palomar telescope in the upper left. The upper left picture is taken in the daytime. You notice the dome is closed and the astronomers are asleep. The stars are still there, right? But you can't see them because the sky is very bright due to scattered sunlight. And that's what's shown in the picture day, this little cartoon here. Now next to it, there's a cartoon showing the brightness of the sky in the infrared during the day. And that's very bright because the sky is hot and the telescope is hot. And you're looking through the hot sky off of a hot telescope. You see a lot of infrared radiation before you have any chance of seeing anything outside the atmosphere. When you come back at night, you'll notice that the dome is now open and the astronomers are working and they're getting images like this the Orion Nebula again with Betelgeuse in its excited state. And that looks pretty great in visible light. But infrared light, the sky is just as bright as it was during the day because it hasn't cooled off at all. So if you really want to do the highest quality, most sensitive infrared work, if you want to work at night in the infrared, you go into space and you cool the telescope. You're in space, you have no atmospheric emission, you can see the entire infrared spectrum, and the cooled telescope means there's no instrumental foreground as there is from a warm telescope on the ground. And that's what Spitzer has done, and that's what made Spitzer so powerful scientifically. The image there is actually an image of the Orion region from an earlier cryogenic infrared telescope in space called IRAS that you may have heard about. So now a quick introduction to Spitzer. I sort of set the stage here. Here we go. So Spitzer, as I said, it's NASA's great observatory for infrared astronomy, was launched in August 2003, more than 16 years ago, into an Earth-trailing orbit around the sun. This is actually quite important. So Spitzer is not going around the Earth, it's going around the sun. And the reason we want to do that is because the Earth is a pretty major source of heat. And it's much easier to get your telescope cold if you're far from the Earth than if you're near the Earth. And in fact, because we're far from the Earth, and because we can always keep the telescope oriented so that the solar panel is pointed at the sun, we can use the back of the telescope as a big radiator, and it radiates into space, into the cold blackness of space. And that means that the telescope is cooled largely by radiative cooling. And when we ran out of the liquid helium we took to get us cold at first, it stayed cold. So here it says, cryogen depleted, warm mission starts. The green part of the trajectory, we had all of our instrumental capability with cold instruments. Here in the latter part, we're only using a limited number of instruments, limited measurement capability, but still able to do really phenomenal science. Here is the end of 2019, that's where we are. This picture is what you would see, I should have said, if you're fixed above the pole of the Earth. You just watch Spitzer moving away. And next month, the end of January 2020, less than 2 weeks from today, we'll be putting Spitzer to sleep. A bittersweet day, shall we say. The text on the left tells us Spitzer's an 85 centimeter cold telescope. It covers a wide wavelength range with both imaging and spectroscopy, can take pictures and obtain spectra. We use large detector arrays, kind of like your cell phone camera, a little more expensive and fewer pixels, but a big advance for the time, and that allows us to cover large regions of the sky very effectively. Spitzer is more sensitive, even though it's an 85 centimeter telescope, than would be a 10-meter telescope on the ground working at the same wavelengths. The impact of that reduction of the sky brightness is so profound that it allows us with Spitzer to do things that would otherwise be impossible. And as I say there have been almost 10,000 refereed papers based on Spitzer results.
Could you compare what you just described with what we'll expect with the Webb?
Yeah, I'll do that. I'll touch on that briefly. Peter will talk about it as well. But basically, the Webb telescope will have 50 times the collecting area of Spitzer. It will cover a wavelength range which includes some visible light down to about 0.5 microns and some infrared light out to about 25 microns. Doesn't go as far into the infrared as Spitzer did, doesn't go as far towards the ultraviolet as Hubble did. And in that wavelength range that it operates in, it will have instruments both for imaging and for spectroscopy. So it'll be very, very powerful scientifically. And we can talk more about that later, but that's a good question. That's sort of the view from 30,000 feet. Okay, so just quickly to go through a few of the Spitzer science results. Because of our large detector arrays, we're able to cover large areas quite effectively, and that's what's called doing a survey. So here on the left, this whole story is a survey of a region where stars are forming. The region on the sky is about 20 times bigger than the full moon, just to get you in the right frame of mind. On the left, we see a number of kind of shell-like structures which were carved out in the cloud of dust and gas within which these stars are formed by either exploding stars or very active stars with stellar winds, which are pushing stuff around. And unfortunately, you can't see it too well, but the little postage stamp in the middle is the famous pillars of creation from the Hubble Space Telescope to the same scale, because we see some of the same phenomena. The little box on the left, blown up to the right, shows in detail the positions of a number of young and forming stars, which we found in this region. And you can see that the green symbols are young stars. They can be identified by their infrared signatures. Again, this is all in the infrared. The yellow symbols are really young stars, okay? And so my explanation of what's going on here is that there's a wave propagating downward where the stars which are producing these cavities are eroding the interstellar material and blowing it away. As they blow it away, they leave behind the stars that have just formed there, and that's the green stars. And in places where the material is more robust, like the mesas and so forth in the Southwest desert, it stays there, and the material isn't blown away, but instead the compression of that wind and maybe the adjacent stars induces the formation of yet another generation of stars. So if we came back in a few million years, the objects that are now colored yellow would be colored green. The whole red structure, red because of the hydrocarbon emission, would have moved down a little bit, and a new generation of yellow stars would be in place.
So we'll have that talk a million years from now on the last Friday of January.
I'm there. Yeah, sign me up. Okay. In a little more detail, we now know, because we know from the Kepler spacecraft, exoplanets are very, very common. You can bet that any star you see in the sky has got one or more planets associated with it. And those planets and that planetary system thus must form as the stars form. And that all takes place in a structure such as that shown here, which we call a protoplanetary disk. So as a star collapses in the interstellar medium, a cloud collapses to form a star. Because of the conservation of angular momentum or spin, a disk will form around that forming star, and that disk will give birth to a planetary system. We know that happened in our solar system because all the planets go around in the same direction, and they're all confined more or less to the same plane in space, which is the plane where that disk was 4.5 billion years ago as the solar system formed. Okay. I'm going to skip over the next slide, which just tells how we can determine the composition of this material. And in these disks, we see interesting organic and pre-organic materials. So we see the stuff of life, if you like, being incorporated into a new planetary system. And this is not at all unusual. Disks like this are seen around thousands of stars by Spitzer. Now I want to talk about exoplanets, which is the big, exciting field of science which grew up with Spitzer. Spitzer's made major contributions to the study of exoplanets. The problem is shown here, where there's the sun and there's the Earth next to it to physical scale, not right distance. You can see that the star is much, much brighter than the planet. And so the way you find the planet, up to down for the most part, is by seeing the effect of the planet on the star. And one of the best instances of that is what's called a transiting planet. Because there are so many planets around stars, a goodly number of them have their orbit edge on as we look at it. And here's what we see when we look at the light from the planet plus the star edge on. There's the planet going around the star. In just 1 second, it's going to go in front of the star. And when it does that, that's what's called a transit. And when the planet transits the star, there's a brightness in the light from the star, which tells us something about the size of the planet. And if that occurs regularly enough, say every 3 days, you know there's a planet of this size in a 3-day orbit around that star. Using this technique, we with Spitzer were able to show that there's one star called TRAPPIST-1, because it was the first star found by the TRAPPIST survey, which is actually home to 7 planets, 7 Earth-sized planets. You know the size of the planets from the fraction of the starlight that they block. You know their position from the duration of their orbits. And from that, we know that at least 3 of these planets are in what's called the habitable zone, the region around a star where water would be liquid on the surface of the planet. And it's thought that that's a really prime place where life might have might conceivably form or have formed at some point. If I go on back to my little animation here, here's the planet going around the star. Now watch what happens when it goes behind the star. When it goes behind the star like this, if the planet is bright enough to produce its own infrared radiation, when it goes behind the star, that infrared radiation is no longer seen. And that drop, seeing that drop corresponds to seeing the infrared light from that planet. And Spitzer was the first telescope ever to see light from an exoplanet, from a planet around another star. Finally, as it moves towards what's called the eclipse, you can see that more and more of the star-lit side of the planet becomes visible. We think these planets are tidally locked to the star, and so here we go again. We're seeing more and more of the star-lit side of the planet, and when we make those measurements and sort of unscramble them, we come up with something like this, which is actually the temperature distribution on the surface of that planet. Okay, and to me, as I was saying earlier, it's easy to get jaded in this business. You know, we deal with amazing things every day. But to me, it's absolutely amazing that I can sit here with a straight face and say, look, that's the temperature distribution on the surface of a planet 40 light years away that I have never actually seen. Okay, I think that's just wonderful. And in this case, there's a displacement. The hottest point on the surface of the planet is not where those two arrows would intersect. That's the substellar point. That's the point where it's always high noon on this tidally locked planet. But the hottest point is displaced from that, and we think the reason for that is that the heat of the star, which falls onto the planet, is transported through the atmosphere of the planet by winds before that heat is re-radiated. So not only do we understand the temperature of the planet and the temperature of its atmosphere, but we can even make informed speculations about the character of the heat transport and the physical properties. This whole field of characterizing exoplanets is one that Spitzer has really pioneered and dominated.
Is that a Neptune or a Jupiter planet?
This is what's called a hot Jupiter. Okay, so it was one of the first and therefore best studied exoplanets. Finally, you were talking earlier about the James Webb Telescope. You might ask, what is James Webb going to do from the point of view of studying exoplanets? This figure shows the planned exoplanet observations by James Webb. Not all of them, but some that are already in the hopper, so to speak. The x-axis is the planet mass. You can see it extends from an Earth mass down to at the far left to the mass of Jupiter here. And the vertical scale is the radius, or the temperature rather, which is as little as a few hundred Kelvin for the coolest of these planets, and then up over thousands of degrees for the hottest. There's quite a variety of planets, and this is only a very small sampling of the thousands of planets that have been seen. Those which are circled have been studied by Spitzer. So Spitzer is an important precursor for the James Webb Space Telescope observations of exoplanets. And finally, if we look in detail at the lower left segment of that picture, we see what we show here. These are planets now which are very Earth-like. Their mass is about the mass of the Earth. Their temperature is a few hundred degrees Kelvin, like 300 degrees Kelvin, as is the temperature of the Earth. And with Spitzer's pointing the way, with James Webb, we're on the verge of studying and searching for biological signatures on Earth-like planets around nearby stars. So that's the end of my part of the story. I'm going to transfer now from these very nearby objects to the most distant portions of the universe, which Peter will now tell you about another area where Spitzer has made major contributions. Thank you.
Thanks, Mike. It's really fun to be here in the Nimoy Theater at Griffith. It's just sort of awesome just walking into the. We had plenty of time, unfortunately, to admire it from about 100 yards away as we were waiting to get in. But,
Yeah.
I do want to emphasize something that Mike was touching on just there. It was an exciting time when we were planning Spitzer in the 90s, but it's even more exciting today, and Spitzer has a lot to do with that. And we're on the threshold of really being able to say if there is life beyond Earth. Maybe we'll find it on these exoplanets. Maybe we'll find it in our own solar system. But we're not, I don't think we're that far away from that. And similarly, we're not that far away from seeing the very first light in the universe. That's what this slide is meant to illustrate. This is a visualization of the history of the universe from the Big Bang to the present day. And so you see at the bottom of a couple of axes. One is time since the Big Bang, going from 0 right at the Big Bang up to the present day, which is 13.7 billion years after the Big Bang on the right, when galaxies such as our own and stars and planets and us are around. You also see a scale called redshift. And so as Mike was saying, the light that was emitted earlier on in the history of the universe expands along with the universe, and that expansion factor, the amount by which is expanded, is called the redshift. And so if we look way, way back to only 300,000 years, 380,000 years after the Big Bang, we're looking at about a redshift of 1,000. Light from that time, 380,000 years after the Big Bang, has expanded 1,000 times, as has the universe since that time. Okay, so Spitzer's actually brought us quite close to that first light, and I'll say more about that in a minute. I've said all that already. And yes, important. So our main way of measuring distance to these distant objects that are not 40 light years away, not 100,000 light years away, but millions and actually billions of light years away, is by measuring how much the light has expanded, by measuring the redshift. Okay, I'll go over that again for anybody who hasn't quite got redshift yet. It takes a little while to get this. I know for some of you it's all that, but not for everybody. Okay, so let's start with some nearby galaxies. Laura, I think, showed this one, a slightly different color map here, but this is one of our very favorite galaxies, Messier 81 in the Big Dipper. A really beautiful spiral. These are Spitzer pictures, and what we're looking at here in blue light are the shorter Spitzer wavelengths taken at 3.6 microns and 4.5 microns with the infrared array camera. And then in the yellow and green here, we're looking at light that goes out to 24 microns with the multiband infrared photometer for Spitzer, originally for Certif. I have my Certif shirt.
I was going to comment. Your shirt, I'm going to interrupt long enough so now you've referenced it so people know what you're saying. The shirt says Certif, which stood for Space Infrared Telescope Facility, right?
Originally for Shuttle Infrared Telescope Facility, and then for Space Infrared Telescope Facility, cleverly. And then after we launched and were proven to be fully functional and didn't have any spherical aberration or any other problems, the Spitzer family agreed to renaming it after Lyman Spitzer, the famous astronomer who actually was essential to the development of the Hubble Space Telescope. Yeah. So what we're seeing here in blue is 3 or 4 micron wavelength light that comes from older stars, and it gives an idea of how much stellar mass is there. What we're seeing in the yellow and red is from younger stars, actually from the dust around younger stars, and we see these dusty star-forming regions strung out along the spiral arms. Mike likes to say like ornaments on a Christmas tree. It's really quite a beautiful picture. M81's neighbor is M82. Messier 82 is a starburst galaxy, and it is undergoing a tremendous burst of star formation. Here we're seeing in red those polycyclic aromatic hydrocarbon molecules, little dust particles that are being excited by ultraviolet light from forming stars. And those dust particles are actually literally being blown out of the center of M82 by a starburst, a very active starburst. And so it's thought that M81 and M82 interacted, and because of the relative spin of the two galaxies, gas flowed into the very core of M82, the one shown here, and caused this starburst, whereas in M81, the one I showed a second ago, it just sort of enhanced the star formation in the arms. And then here's another beautiful Spitzer image. Here we're looking at the Sombrero galaxy, Messier 104, I believe. And this is almost like a hybrid of two different galaxies, an old spherical bulge of a very massive galaxy, actually much more massive than our own, and then a star-forming ring, perhaps the result of a merging system.
So just to reemphasize, all that blue light is all stars.
That's right. And
because it looks almost like it's a vapor, but it's all stars.
Yeah.
If we could look with high enough magnification, we would start to pick out individual stars there. Now, if we look, one of the things that Spitzer could do actually was take images with its spectrograph in spectral bands, and that's shown in this image here. And that shows us that when you look in the wavelength of the polycyclic aromatic hydrocarbons, you just really see the ring, and that tells us that that ring is red. It's not just putting out continuum emission from warm dust, it's actually putting out the spectral features that are associated with those dust particles around forming stars. Okay, this galaxy is about 30 million light years away, but I'm going to now step out much farther. And before I do that, I want to explain where, remind you, I've already talked about this once, but let me say again where this light is coming from. So the black line here is the overall brightness distribution of a typical galaxy. You can see the wavelength on a log scale going from much shorter wavelengths than we see, 0.1 microns into the ultraviolet through to 1 micron, so that's kind of the visible range, then out to 10, 100, and 1,000 microns getting out into the infrared and even a millimeter wavelength range. And what we see is two peaks. This is the camel that has two humps. The shorter wavelength hump is the one that we saw in blue in the image of the sombrero a second ago. And that's coming from stars, evolved stars. And measuring the amount of that light tells us the mass of stars that's there. The peak on the right, which I think I can do this without disrupting too much there. So this one is coming from warm dust, and that is associated with forming stars. And Spitzer, you can see the Spitzer wavelength band kind of straddles both of these. The other thing that you see, let's see, so again, it's light from 1 micron coming from mature stars, telling us the stellar mass, the light from the longer bump coming from warm dust, and then the wiggles in the middle also coming from those polycyclic aromatic hydrocarbons that I showed the spectral image of a moment ago. And Spitzer has the ability to measure both of those. Now the red curve says, well, what if we put this galaxy far, far away, so far away that the universe has expanded a lot since that light was emitted. The light has expanded by 200% in this example. We call that a redshift of 2, 200% longer wavelengths than what started out.
So you're saying that's a galaxy far, far away a long time ago?
Yes.
Absolutely.
Exactly, yes, actually about 10 billion years ago. So,
very good.
Is there a
Laura.
spectral signature of buns, hair buns? So, no. Please keep going. I apologize.
I don't know, there might be a Jabba the Hutt somewhere in there. But what you see is that the light from the stars, the bump on the left, try and do this there. This guy is really shifting into the Spitzer band, okay? And so actually these distant galaxies are in some ways getting easier to see as they get farther and farther away. And at the same time, it's dropping like a rock at these shorter wavelengths, which are the visible wavelengths that you look at with telescopes, optical telescopes like the 200-inch or Hubble. And so Spitzer is very, very powerful at looking at these features from distant galaxies. And that's, right, so this point is being made again here in words in case I forgot to say it. So obviously the further away the galaxy is, the bigger the shift is. And the most distant galaxies really can only be seen in infrared light. And I will show you an example of that in just a couple minutes. But here is a reprise of that picture that Mike showed. This image was taken with the Kip Peak 4 meter. It's about an hour exposure in optical filters. And then this picture on the right was taken in 90 seconds with Spitzer, which is not a 4 meter telescope. I think I saw somebody up there holding up their hand. It's about like this. It's sort of a hula hoop size telescope. So, and it's this cryogenic telescope in space, but also the fact that the redshift is pushing the light into the Spitzer's band. So infrared is really crucial to seeing the early universe, looking back in time towards the first light. Here's a little more detailed example of a more distant field. If we want to look far, far back, the example I just showed was about 8 billion light years away. This is the Hubble Deep Field, which I'm sure is familiar to many of you, as seen with the Hubble telescope itself. Hubble exposed for about 10 days to get this picture, and because of this need for infrared light to see the most distant galaxies, astronomers worked really hard. David Hogg and his colleagues worked really hard to get an infrared picture from the ground with the Keck telescope. They spent about 10 nights trying to get this picture in the middle at infrared wavelengths at about a 3 micron wavelength. And, well, they saw a few things. It's, this is a negative image just in case you're wondering. So the black dots there are detections. Spitzer spent a few days looking at this, and this is what we found at 3.6 microns. And so I think you can see that the patterns are very recognizable at 3.6 microns. But Spitzer didn't just image at 3.6 microns. He also did 8, 16, 24, and 70 microns. And so with these measurements, we're able to measure both the amount of stars that there are in these distant galaxies and the amount of star formation. And that's really been critical for our understanding the history of star formation over the lifetime of the universe. So this is, as I was saying, Spitzer has been measuring the star formation history of the universe. And that's from measuring that longer wavelength light at 24 microns in particular. And Herschel has also measured that. Herschel is an infrared telescope that the Europeans launched in 2009, I think.
Approximately, yeah.
And it's a bigger telescope than Spitzer. It stopped operating in 2013, but it could go to somewhat longer wavelengths and carry these star formation measurements out a bit further than Spitzer could. And so with those measurements, we're able to assess how much star formation there's been going on versus the age in the history of the universe. So on the top of this plot here, we're seeing how far back in time. So here we are today at 0 years from now, looking back 2, 4, 6, 8, 10 billion years, or in redshift 1 or 2. And 10 billion years ago, what we see is that the cosmic star formation rate was about 10 times higher than it is today. So the universe was really hopping 10 billion years ago. Astronomers sometimes say that we're in cosmic dusk today, and this peaked 10 billion years ago was cosmic high noon. And then an interesting thing happens. I mean, this is pretty interesting to start with, but then it actually starts to drop again, at least as best we can tell. Here we're limited more to measurements with optical telescopes because the redshifts are so large that even Herschel couldn't measure them. Nowadays, there's a millimeter telescope in Chile called the ALMA telescope that is giving us some idea of what's going on with star formation in the infrared at these very early times. Okay, the other thing to notice here is that black line is just a mathematical approximation of the data points. It's just sort of take a simple mathematical function and say, okay, well, this goes through the data points pretty well, all right? Now we're going to look at the other thing that Spitzer measured, which is the stellar mass. Okay, again, we're starting with stellar mass today is about a little over 10 to the 7 in these units. Solar masses per million cubic light years, I think. Yes. And not surprisingly, as we go back in time to the right, or out in redshift to the right, what we find is that there was less and less stellar mass because fewer stars had formed. Okay, and it drops actually by a big factor. You can see it's about 100 times lower back at the right side of this plot over 12 billion years ago, getting close to the Big Bang. What's really remarkable to me about this is, well, it's really neat that we can make this measurement. And this is almost all Spitzer data that was used to make this measurement. But what's really remarkable is that black line is not a fit for these data at all. That black line is just the same black line I showed in the previous slide, converted into stellar mass. And so if you know how fast stars are forming at each point in the history of the universe, you can say, well, okay, we're forming stars at 10 solar masses a year. After a year, we're going to have 10 solar masses. After 2 years, we'll have 20 solar masses, and so on. And you just add that up, and you get this black line, which gives you the stellar mass over the history of the universe. And so these two measurements actually, amazingly to me, agree with each other remarkably well. And so this really gives some confidence astronomers might actually know what we're talking about here when we talk about the star formation of the universe. And Spitzer's really been central to this. So I'm going to close with a view of the most distant galaxy that we know about, which is not a redshift 2 or 4 or 8, but actually 11.09 in fact. It's so far away that, as I said, it completely disappears in visible light. And we're looking so far away that we're looking to when the universe was only 400 million years old, which sounds kind of old, but it's only 3% of the age of the universe today. So it's really, it's infant years. And so here is an image, not just in visible light where it doesn't show up at all, but even at 1 micron from the Hubble Space Telescope. Pretty deep exposures. you don't see much of anything. You have to go all the way out to the longest wavelength that Hubble can observe at, which is 1.6 microns. And this is, by the way, in the James Webb wheelhouse, these kind of wavelengths. And there it pops up nicely. And what's happening is that the light has been redshifted, expanded so much that we're looking far, far into the ultraviolet wavelengths, less than 1/10 of a micron, until we get out to 1.6 microns here on Earth. That light started out at about 0.1 microns, 0.12 microns in the galaxy. Now that's still far in the ultraviolet. If we want to have some idea what this galaxy is doing, we want to see something like visible light, and that's what Spitzer can do for us. And here we see it just comes booming through in a admittedly 100-hour exposure. Actually, I think it might be 200 hours for this particular galaxy. But the thing is that, so Spitzer's seeing it, and so first of all, it's telling us there's not just a blip here, there's actually really something there. This isn't just a mistake. There's actually something there, which is good to know. I wrote a paper once on a redshift 10 galaxy that turned out not to be there. Actually, the paper was on the galaxy not being there, which didn't get much attention. People don't want to hear that.
That's right.
But Spitzer's reaching out almost into the visible range. This redshift is so big that even at 4.5 microns here, we're only getting to the light that's a bit bluer than our eyes can see. But still enough into the visible that we have some idea of what this galaxy is up to in terms of its age and its mass. It's surprisingly massive, given that we're looking so far back and close to the Big Bang. And maybe not surprisingly, it's not very old, less than 50 million years. Okay, and all of this is exactly the kind of galaxy that the James Webb Telescope was designed to go after. And yeah, that's a big one. Those are real people standing there in the, I believe it's the thermal vac chamber in the Johnson Space Center in Houston.
And I love the size of that door.
Yeah, yep.
Yeah.
And so I was talking to John Mather at the American Astronomical Society meeting, and he said things are going pretty well, but there's still another year before James Webb hopefully launches, and hopefully all the complicated things that have to go right will go right. And there are a lot of them, so there'll be a lot of tense moments there before this is fully deployed. But it's very exciting times, and Spitzer has really played a tremendous role in, first of all, showing that there are galaxies that will be straightforward and exciting for James Webb to study, and maybe more importantly, finding, because of its ability to survey large regions, where some of those best targets for James Webb will be. Because James Webb is extremely powerful, but it's a bit of a battleship, and repointing it takes a while. And it can't map out large regions. And Spitzer, in contrast, is mapping out quite substantial regions. And so we've done our biggest survey ever, taking the better part of a year of Spitzer time, picking out the galaxies that will be best for James Webb. And so I want to close by thanking you for listening, and of course we're happy to answer questions, and we'll be signing copies of the book, and we don't get any royalties, in case you're wondering. But I really want to close with this epigraph from that sort of brings us back to the beginning. With that Redshift 11 galaxy, I think we might agree that Spitzer has brought us very close to the first light in the universe, and that inspires this epigraph, which is near the end of our book. What we call the beginning is often the end. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. Thank you.
Thank you.